The theme of this conference is Advancing Precision Agriculture in the Age of Artificial Intelligence. And now Dr. Raj Khosla has talked about how AI will transform precision agriculture. And now at the University of Minnesota, a lot of scientists are working on AI for precision agriculture. And now we would like to invite Dr. David Mulla to talk about AI for precision agriculture research at the University of Minnesota. Yeah, welcome, Dr. Mulla.
Thank you very much. I'm very honored again to be here to speak about our research in AI for agriculture and particularly precision agriculture. So I'm representing the Precision Agriculture Center as a board member now, and also I'm the co-director of the AI Institute for Land Economy, Agriculture and Forestry, which is a USDA NIFA supported project, which I'll be talking a little bit about. Raj did a very good job of describing what is artificial intelligence, and you know, machine learning is a subset of that. So I'm not going to go into a lot of detail on this. So there's been some recent policy papers on AI in agriculture that are either just recently produced or are in the process of being released. One is a Council for Ag Science and Technology document on AI in agriculture. And the other is an AI for Agriculture Collaborative Vision document, which was created by the 5 AI institutes that are funded by USDA NIFA. So, and I had a role to play in the second one here. This first one was led by Alex Thomason, who's now down in the southern part of the US. But some recent conclusions out of these papers are that, yeah, people are really ready and able to use AI, but they have these issues of, is it trustworthy? Can I trust it? So that's something, you know, we can write programs to do the data processing, but is there sufficient, attention being paid to privacy and security? Also, computer scientists can't just sit in their offices and write code and expect that farmers are going to use that code. You have to have some kind of co-creation process where the farmer or the producer or the agribusiness person tells you a little bit about what problem needs to be solved and what their constraints are. Third very big barrier is benchmark data sets for training and testing. And these have to be relevant to precision agriculture. And there aren't a lot of those available. You may have data sets for individual fields, but that's not exactly what's needed for this new era that we're in. We need, that data that you got in your closet, Dean, those disks that, those floppy disks I know that came from the 1980s. They have a lot of data, but somehow we need to compile all those into a big database and start mining them. And in the education and workforce development is a very big issue. We don't have enough people that really understand what's happening to be able to go out and use this on a routine basis. So those are some of the takeaways. There's lots of potentials for AI in precision agriculture and agriculture in general. And it all comes down to how can we improve good decision making. And that really relies on reducing the uncertainty and addressing the spatial and temporal variability that we have. There's lots of different ways in which we can apply data to make better decisions. And Raj, talked a lot about some of this, so I don't need to spend time on it. Decision making in agriculture, is really focused on the farm and on the management practices and decisions that have to be made at the farm. And these decisions can be made in real time or days, weeks, or even months in advance. However, what we have to think about with AI is the idea that decision-making, really the tools for this have to be developed by thinking about what's happening on many, many, many thousands of farms. And that's how AI learns, is by looking across large regions with many different soil types, many different types of management, many crop rotations, many climatic factors. And so we have, the temporal dimension and the spatial dimension, and a lot of the data that we actually need to make these AI models work are going to have to come from coarser decision scales, like counties and states and regions and nations. That's the kind of data that is used to train a lot of models. There have been some good, really success stories recently about how AI is used in agriculture. So we have John Deere's See and Spray, and Rod showed some photos of little robots going through the field and, controlling weeds. But you can do this on a bigger scale with large farm implements. Syngenta has some very interesting AI-driven recommendation systems that they call CropWise, which I think are very advanced. Bayer has a generative AI co-pilot that can do exactly what Raj was showing on the phone, where the person asks the chatbot, what should I do? That actually exists now and is being marketed by Bayer for farmers to make decisions. And if you want to know the story behind that, I know the story behind that. It's very interesting. Small startup company, located here in Minnesota called SIBO is using AI-guided computer vision and ecosystem modeling for agricultural sustainability. And then we have many multinational corporations that aren't traditionally thought of as agricultural companies who are developing large language models that can really be applied in agriculture. IBM, for example, has developed Prithvi WC Foundation model to make weather forecasts. And these weather forecasts are available anywhere in the world, and they can actually do a very good job of predicting the future weather out to 3 to 10 days. So the uncertainty of these weather predictions today is quite low. I mean, that's really what farmers want, is like low risk in assessing what's the climate, what the weather's going to be in 3 to 10 days when they have to make a decision. So if you combine that information with an AI model, that tells you about irrigation or when a crop pest is going to be likely to occur based on weather conditions, you can get an accurate idea of when to spray and where to spray, products. USDA Agriculture Research Service is really accelerating their efforts in creating AI and machine learning tools for agriculture. And last summer, we had a chance to meet with the director of the ARS, and he showed us this graph where you can see the areas of agriculture where AI is now being used. A lot of it is on water availability and watershed management. And another big area is, food animal production. And then you have these other smaller areas, food safety and things of that nature. So the AI is being used more and more by the researchers, and these tools will eventually filter down into the commercial area, into industries. So a lot of people are now asking questions like, are producers going to start using AI? Do they trust it? And this is, a survey that was done by David Ebert from Oklahoma State University. And he surveyed producers to see how much they trusted AI. And so there were a couple of questions. One was, have you heard about AI, and have you used it? Well, it turns out that quite a few people, yes, they've heard about AI, and they haven't used it. This bar here is a little bit more interesting because these are the users who, you know, they say, yes, I know about it and I am using it. So we have, and these are broken down by region, so you can see like in the Midwest, which is the blue colors, 29% of farmers that were surveyed said, yes, they've heard about AI and they're using it in their actual farm operations. That's astonishing. All right, and then the second set of questions is, you know, do you trust it? And you can see here that the majority actually have somewhat strong trust that AI is going to help them make better decisions. So this again is very promising in terms of the likelihood of getting people to adopt the tools that are developed. Bruce Erickson, who's a member of our AI Leaf Institute, has been now starting to ask questions of the retailers, the dealers, about the impacts of AI in agriculture. And so for example, does automation have the potential to increase the accuracy of recommendations? 55% of the crop retailers who are providing services to farmers say yes. And 54% say automation will help reduce mistakes. And then 45% say AI will lead to better agronomic recommendations. So these are all very positive things. What's less clear is the economics. So there's not as much data about the economic impact of adopting AI. And I think this is a very big area where the researchers could, you know, add information to help promote the idea that yes, AI can actually lead to better profitability. If we start seeing some studies of that nature, then I think the adoption rates will go up. There are data issues, as I mentioned earlier. You need large amounts of data to train AI models. The old way of training was called supervised or semi-supervised training, and that requires very large amounts of data, which has to be, by the way, labeled. You have to have ground truth data that's labeled. Today, there are lots of new AI techniques being developed that are not supervised, meaning that the data don't have to be labeled, and you can get away with using less amount of data when you have those new tools. These are, so the whole, and I'll talk about this later, the whole idea of transformers is a way of doing this a new kind of training which doesn't involve supervision. We do need data from, you know, public sources over large areas. These are like the statistical services that the USDA provides. Those data are essential for doing some pre-training of large language models and foundation models. But then we need to take those large language models and foundation models and refine them with data from private farms. And this is the part of the chain that's not yet well thought out or developed, okay? So this is an area where a lot of work is ongoing and where a lot of advancements are likely to be made. So the large language models and the foundation models are trained and tested on generalized data and basically on short-range climatic data. I think what we need to do is go back to this third bullet and you know, do the fine training for what's now being called small language models, which are the refinements of the large language models. So there's lots of advancements being made in AI. However, all of this takes more and more computing power. And so if you look at the number of parameters that some of these large AI models use, they're in the millions, okay? So I'm working with students right now who are training models. We're trying to decide, should our model have 1 million parameters or should it have 6 million parameters? Honestly, these are the kind of questions that this new technology can deal with. It's not like the old way of doing computer modeling where we had 100 parameters that we needed to calibrate. All right? It's a whole different world. And the computing power that's needed to do this is unbelievable. Also, here is the problem that we're running up against. The largest supercomputers in the world today are no longer able to supply the speed of calculations needed for training these new models with so many parameters. So we're getting out of the envelope of what is actually possible to train. And this comes with like energy costs as well. You know, it takes a lot of energy to run these models. Okay, so with that, I'm going to kind of talk about the progression from simple machine learning models to very complex AI models. So we'll go from random forest and support vector machine, which is used for classification and regression with small databases, to foundation models that can be used at large scales for very versatile downstream tasks, anything from insects to fertilizer to irrigation to flooding to weather prediction. They can do many, many tasks, not just a single task. And then in the middle, you have more finely trained models that can actually make decisions on specific tasks. So I'll talk a little bit about that. And then in the second from the bottom, of course, everybody's interested in chatbots, and co-pilots and how those perform. So I'll talk about all those things. So let's start from the beginning. The simplest machine learning is really the artificial neural network. Now, Yuxin Miao and myself and Pierre Robert, in the early 2000s, we actually were working on an artificial neural network model that was trained on data from several farm sites in Illinois. And so this was a really big advance. We have, a neural net model that has an input of, whatever you sample, the yield or the soil moisture. You have a hidden layer, a neuron, and you have an output layer which predicts. And you can bring lots of data into this model, and the elevation, the aspect, the soil moisture, the yield, the soil nitrogen, the phosphorus. You can just put it all into the same model and come out with these really accurate recommendations for a given farm. The problem is, how do you use this model the next year or in the next field? That was the problem. You can't really do that with these early models that are finely tuned to a specific field, okay? So the next advance is the deep neural net, DNN. And here you have multiple hidden layers, which is where the number of parameters starts to increase. You can have many, many layers here. And that's where we get like 1 million parameters to define the weights for all these interconnections between the input layers, the hidden layers, and the output layers. That's what we mean by the parameters. So just think about how many nodes and connections there are in these models, and those all have to be evaluated and parameterized. So with this additional depth, you can get additional accuracy. There's some really good examples of how this is used for, weed management and things of that nature. And then the deep neural networks themselves are divided into two broad categories, which I want to talk about. Convolutional neural networks, which are usually associated with image analysis. So if you want to know how many fruits there are on an orchard tree, or recurrent neural networks, if you want to know how soil moisture is evolving over time. These are two completely different kinds of tools that are both classified as deep neural networks. So how do they work? The recurrent neural nets are designed to handle time series data. So you have a set of inputs, which are your X values. At different time, it could be soil moisture, it could be weather. And you basically, develop a model that advances over time. You make predictions of your outputs over time. And, this process is very good for estimating the future soil moisture or the future biomass of the crop. The problem with the recurrent neural network is it doesn't have any memory. Okay, it doesn't remember what happened in the first time step. So another advancement in the recurrent neural net is to use long short-term memory. And here what you do is you actually keep some memory of the initial states. Like what was the antecedent moisture content? What was the initial biomass of the crop when you started doing the modeling? And you can use some of the data. You don't have to use all the data that was from that initial time step. So you have a forget gate. All right, this is really good for old people. We don't want to remember everything that we did, 30 years ago, 40 years ago. My God, there's a lot of stuff that we can just forget about. But there's some stuff that we still need to remember and keep in mind because it was valuable. And so we want to propagate that through the time series of this process. And that's what this does that's different. Here's an example of some work we did out in California to map the different crop species in the Central Valley of California, which is very diverse and has a lot of minor crops. If you go to the USDA National Ag Statistics Survey, their estimates of the acreage of different minor crops in this area, and in fact, over the entire US, is quite suspect when it comes to minor crops. So we worked on a lot of minor crops. Corn, of course, is not a minor crop, but the point here is by using this recurrent neural network that is based on time series of remote sensing images from satellites, we can estimate, based on the different phenology of the different crops, which crop is growing where at what point in the year. And to train this model, you can see here we needed about 57 million data points. Okay, so training these models is very, very labor intensive. But the accuracy that you get is pretty high. So even with really minor crops, like grapes, you get an 82% accuracy. And this is phenomenal because we could never do that in the past. Okay, now I'm going to go over this one real fast. The recurrent neural nets are a little bit unsophisticated when it comes to using computer memory and processing time. So to increase the efficiency of the computer, this other type of RNN called gated recurrent units combines the update gate and the reset gate. So it's combining two functions in the neural network model that relate to memory. And that results in fewer parameters and more efficient processing in the computer model. All right, another big breakthrough in artificial intelligence was made right here at the University of Minnesota called knowledge-guided machine learning. And Vipin Kumar is the person who really kind of spearheaded this advance. He's in the computer science and engineering department. What this does, in a typical neural network model, you put a lot of data into it, and then the model, is fit using statistical techniques, weighting and all that, of the neural nodes. And it's just statistics. So if you try to apply that model somewhere else beyond where it was trained, it often doesn't work well. The reason is it doesn't incorporate any physical knowledge about the processes. It doesn't know about mass balance or conservation of mass. It doesn't know that the nitrogen minus the nitrogen taken up by the crop, minus the nitrogen leached, minus the nitrogen volatilized. It has to be in balance. But with knowledge-guided machine learning, we can put those constraints into the model, and we can use that physics-based loss function for conservation of mass. We could do it for irrigation as well, where precipitation minus ET minus runoff has to equal soil water storage. That is used to help the model do a better job of prediction. And so it learns what the kinds of relationships are between rain and water content in the soil, and that's constrained. So you get higher accuracy and you get the ability to include knowledge in prediction. Another big obstacle was overcome with regards to the need to have labeled data. And this is through what we call the ability to have transformers which encode and decode information from time series of satellite images. So you basically take a satellite image, and each scene has spatial dimension and a spectral dimension. You have the different spots on the image, and you have the different wavelengths that were sensed. So what happens when you go through this process is you gradually reduce the spatial dimension, and you find the spectral signatures that are associated with the feature that you're trying to predict, like nitrogen deficiency. And then when you get the spectral signature that's associated with nitrogen deficiency, you rebuild the spatial dimension so that you can use those spectral features to predict where the nitrogen deficiency is occurring in the map. We've applied this to mapping olive trees and distinguishing them from all other types of trees in the country of Morocco, for example. Here's an example of using that same technique where we can identify specific trees. Okay, now large language models and foundation models, I've talked a little bit about that. These are quite important today. IBM and Microsoft and many other companies are rolling out large foundation models based on public databases and satellites. These are the foundations for these co-pilots and chatbots, and the outputs can help guide precision ag. So here's an example of what these tools can do. There's somebody took these chatbots and asked the chatbot to take the exam offered by the tri-societies to technical service providers. And this chat GPT actually passed the exams that technical service providers have to pass in order to get certified to give advice to farmers. It did this with very high accuracy, about 82% accuracy in the initial version and 90% in the next one. Then two additional things happen. If you get retrieval augmented generation of knowledge, which means that you look for information that's new that wasn't used to train the original foundation model that has been developed in the last month. So it just searches for new publications or other kinds of relevant information. You boost your accuracy up, a little bit when you do that. And then if you ask for context, like, is this a farm in Minnesota or is it a farm in Louisiana, the accuracy goes up even more. So these are really stunning things. How much time do you want me to have?
Yeah, you've already passed your time.
Oh, I passed my time, okay.
You can write up.
All right, well, I'll just, let me just give you some highlights then. Here's some examples of how AI is being used. This is for fruit detection using, convolutional neural nets. This is some work that Dimitris Zermas did for his PhD on crop phenotyping, where we could actually take images of crops, separate the crops into stems and leaves and count the leaves, estimate the height of the crop. We could also detect nitrogen deficiency using sophisticated models that could draw boxes around the leaves that actually have nitrogen deficiency. We could develop nitrogen fertilizer algorithms to find out how much nitrogen to actually apply. We've used AI to do phosphorus recommendations in clusters of fields, using a lot of auxiliary data from satellites, conductivity, and then soil sampling at different spatial resolutions. So we have, we're now combining data from, if you just rely on the phosphorus samples, at 2 samples a hectare, you don't get very good maps. But if you have auxiliary data, you can get much better maps. So here's the, 2 samples per hectare type map. And here's the kinds of maps we can create when we have auxiliary data. We see the spatial variability a lot better. And we can make better maps of where, phosphorus needs to be applied. These are the rates of phosphate in kilograms per hectare. This ends up giving us pretty big economic returns. So we can, reduce the P rates by doing the variable rate P and increase the profit substantially for the farmers, depending on which field we're talking about. Xiong has been doing some good research on hyperspectral remote sensing to detect, fungi in wheat, and she'll be talking about some of this research later today. I've been working with an entomologist here in the University of Minnesota to use satellite remote sensing to classify areas that need to be sprayed for aphids versus areas that don't need to be sprayed. And we can clearly distinguish fields that are above and below. So these are all individual commercial fields throughout Minnesota that we've actually ground truthed, and we have an 80%, 85% accuracy. So lots of, really important things, advances are being made in AI. The University of Minnesota is right at the heart of making those advances. It's paying off for farmers, and I think the future is very bright. Thank you very much.